you for that very kind introduction. It's great to be here. I wanted to start off before I tell you about graphene with just this. This is our version of the California Nanosystems Institute. Of course, Santa Barbara is our sister institution. And when we got started, the state gave us $100 million. So of course, we built our building. We spent $170 million. But it has really good microscopes and collaborative space. Okay, today I want to talk about graphene synthesis and applications. And we'll look at different ways of making graphene and what we can use it for. And I'm going to start off just briefly, just remind you about carbon allotropes, how to make graphene, solution processing. We'll talk about sensors, transparent electrodes, and then laser-scribed graphene and supercapacitors. So here's the structure of graphene. And just by show of hands, how many people think their eye's good enough to see a single layer of carbon? A few. That's good. So you probably know that Novoselov and Geim made the first samples of graphene using Scotch tape and pyrolytic graphite. So I'll pass some of this around. I've been passing this around for over 25 years teaching undergraduate chemistry. So here's pyrolytic graphite and Scotch tape. And never in my wildest dreams would I have imagined that you could, if you kept peeling, that you could eventually get down to a single layer. But that actually wasn't the genius of Novoselov and Geim. The real genius is, how do you know you have a single layer? And what they did is they took it and they put it on a piece of silicon with a 300 nanometer oxide coating. And it forms a beautiful interference pattern. And so I'm going to pass this sample around. Now, almost all the samples I pass around you can touch, but my students would appreciate if you don't touch this one because it's actually hard to reproduce. So just look at this, don't put your fingerprints on it. But on the right-hand side, you will see silicon with an oxide coating. We've grown by chemical vapor deposition a single layer of graphene and transferred it to. I'll explain how to do that in a moment. But if you look at this when it comes around, you'll see this interference pattern. And you shouldn't have any problem seeing it. Now, that's actually not seeing graphene, right? That's an interference pattern. But it turns out graphene is the darkest material ever discovered. A single layer cuts down 2.5% of visible light. And so after you identify that, if you look on the left, you'll see a piece of glass with about the same size rectangle of graphene. And if you look through the edge, it's 100% relative transmission. If you look through the middle, it's 97.5. And your eye should be good enough to tell the difference. Okay, and again, it's pretty much going to look like a shadow, but it's pretty amazing that you can actually see this with your eye. Now, an interesting story. A year ago, Konstantin Novoselov was visiting UCLA. And after having a nice talk with him, we went out to lunch at our faculty center. And we had a group of people, and I said, you know, I read somewhere, I have to ask you this question. I read somewhere that some poor graduate student spent 4 or 5 weeks peeling pyrolytic graphite to get the first sample. In his deep Russian accent, he's like, no, this is not true at all. He said it was no graduate student, it was me. So it really did peel. Okay. So if you think about this, you have a layer of sp2 carbon. It's completely flat. And you can think of graphene as a building block for all other forms of carbon. So if you put 12 5-membered rings in, you can get buckyballs. Here's carbon-60. If you roll this up, you can get carbon nanotubes. And if you stack it up, you can get graphite. Of course, graphite's been known since the Middle Ages. When there's mines, you can pull it out of the ground. Of course, these other two came much later in more recent times. But this is credited in 2004. And of course, Novoselov and Geim shared the Nobel Prize in 2010. Now, my own work in carbon, as you heard, began in Neil Bartlett's lab at Berkeley back in the mid-1980s. And at UCLA, after carbon-60 was discovered, one of my colleagues, Rob Wetton, said, if I give you some C60, what will you do with it? And I said, well, I'll dope it like we dope graphite. And so we put potassium in, and by the time we had done these experiments, Bell Lab announced the stuff goes conducting and superconducting. But it turns out that they only had a 1% superconducting fraction. And so we actually had much more C60 than they did, so we made the first pure samples of completely superconducting C60, and we were able to solve the crystal structure. And if you look at this isn't a great picture from the cover of Nature, but here's carbon-60. It's artistic, I guess. And you can see that the potassiums sit in all octahedral and all tetrahedral sites. So if you think of an FCC lattice like sodium chloride where you fill all octahedral sites, or fluoride or antifluoride where you fill all tetrahedral sites, well, here the C60s are big enough that you can screen the tetrahedral and octahedral sites from each other so you can fill them all. So it makes a beautiful, beautiful lattice. Okay. This is my favorite picture of graphite, and this is from Neil Bartlett's lab. And what we're doing is we're hitting a slab of graphite, and this is about the size of your end of your little finger. This is highly oriented pyrolytic graphite. We're hitting it with a laser. A normal material heats up in 3 dimensions, but of course graphite isn't a normal material. Thermal conductivity follows 2 modes. It follows lattice vibrations or phonons, and so that's all the covalent bonds, which are all in the plane. All the sp2 bonds are in the plane. And it follows conduction electrons, and the conduction electrons are the overlap of the pi orbitals. And the pi orbitals all overlap in the same direction. So heat only transfers along this layer. So if you touch here, you burn yourself. If you touch the top, of course, it's cold. And this is the only picture that I've ever seen of basically a molecular scale property in the real world in 3 dimensions. And if I'm wrong, somebody will tell me. So it's a nice illustration of just how 2-dimensional this is. And of course, a single layer would be graphene. Now, there's a lot of history to graphene, and I'll talk a little bit about intercalation exfoliation routes. I mentioned mechanical exfoliation by Novosel and Geim, but there's other ways. Walter de Heer's group at Georgia Tech has been taking silicon carbide and simply reducing it, basically boiling off the silicon and leaving a layer of carbon behind. And then, if you want to make electronic devices, what you really want to do is chemical vapor deposition. And Rod Ruoff's group, he's in Texas, but he's now moving to Korea. And he's done some of the best work in the area introducing copper surfaces for doing CVD. Okay, my own work in carbon started in the year 2000 when one of my colleagues from mechanical engineering, a guy named Tom Hahn, knocked on my door. And I think he knocked on my door because Fred Woodall, who you all know, had sent him to me. And he knocked on my door and he said, I understand you're a resident expert in carbon. I said, well, I've worked on carbon for a long time. He said, good. I need you to make me a single layer carbon. Can you do it? I said, well, I can probably do it, but why would you want it? And so he showed me these mechanical calculations he had done that showed a single layer carbon would be the best reinforcement for polymers because it would reinforce in 2 dimensions instead of 1. So then he's like, well, how would you do it? I said, well, you know, graphite's a layered compound, so I just heat in the presence of potassium. It's been known for many years that if you do this under inert atmosphere, you get a first-stage intercalation compound. The formula is KC8. It's bright gold. I actually should have brought it along. I took it out of my case because if I travel, you're not allowed to travel with it because if you break the seal on the case, it bursts into flames. Okay, why does it do that? Because potassium would rather be, the potassium plus here would rather be potassium hydroxide than stay in the lattice. And so using that idea, I just said I'd hit it with alcohol, and KOH would come off, and we'd blow all the layers apart. So he said, that's great. So we went and did that, and when we did that, we blew the layers apart, and we put it in a sonication bath, we would get carbon scrolls. And if you look here, this is a Lacey carbon TM grid, and here's a nice carbon scroll. And here's a more tightly wound scroll, and here's a whole lot of scrolls. And if you look at the date on this, a lot of people thought we had actually made graphene, but our TM instruments at the time weren't that good, and so we couldn't prove that we had made any less than 8 to 10 layers thick. But if you look at the data, this is a science paper in 2003. So this is the year before Novosel and Geim did their work. Now, I figured that the goal was to make graphene. I figured we probably had made graphene, so I took out a patent on graphene. So I have a graphene patent from 2002, 2 years before it was discovered. It wasn't issued till 2005, still hasn't been licensed. But it turns out people have subsequently shown that this does work. It makes graphene. The only problem is it not only makes 1 layer and 2 layers, but it makes all different layers. Nobody really understands why. But after Novosel and Geim did their work, I realized that if graphene is going to be useful, especially for energy storage, which is what I came to talk about, you need to scale it up. And peeling with Scotch tape isn't going to scale things up. Even doing chemical vapor deposition on copper, you're making a single layer, and all you do is you take a hydrocarbon source, could be methane, and you do it in inert carrier gas, usually nitrogen or argon. You go to 1,000 degrees, and copper has an exceedingly low solubility for carbon. So what you end up is you nucleate just a few spots, and it grows across the surface. And this is in contrast. You know, if you want to make diamond, you do it under high pressure, high temperature, but you use a catalyst that has a high solubility for carbon. So you take iron, cobalt, or nickel, and that works. But if you choose copper, which has a low solubility, then you start getting this. Okay, and this is great for electronic devices, but you're never going to scale this because you're going to waste too much copper in the end. So you're going to need a chemical route. And as a chemist, when I think about this, what you really need is something where you can take something like graphite, turn it into something like graphite oxide, and then turn it back into graphene. And that's what I'll talk about. Okay, first of all, a little bit about chemical vapor deposition. The sample going around that you're actually seeing graphite with your eye, here's what it looks like. Here's the interference pattern. You can see this rectangle on silicon with a silicon oxide. And if you image this, you can use atomic force microscopy, and you can actually see the hexagonal lattice. What's often used is Raman spectroscopy, because if you look, graphite and graphene have a G and 2D peak. And if they're in the 1:4 ratio, that tells you have a single layer. Now, one of my colleagues, Jim Chesky, is an expert in scanning tunneling microscopy. And so we actually were interested in what's going on with this copper surface if you try to grow graphene. And copper is a nice crystalline inorganic solid. So if you look at this STM map, you'll see all the hills and valleys and plateaus. Nice crystalline material. So what happens when you try to grow graphene? When you try to grow graphene on this, it nucleates someplace. And here's an STM map of the carbon. It grows right over one of those hills and valleys. So basically, it nucleates and just grows independently of the material. And if you look here, this is one of those beautiful pictures of graphene that you'll ever see. Because every 6-membered ring, every carbon's there. If you take graphite, you only see 3 dark carbons and 3 lighter ones because of its structure. But here, all 6 show up. All right, I realize from where you're sitting, you're probably saying, that is not a beautiful picture. In fact, what you're seeing is white and red and yellow and all these different colors. But keep in mind that STM measures an electronic density map. And so what you're looking at is electronic density. Well, the carbon is flat. It's essentially perfect. It's the underlying copper surface that shows up in these electronic colors, if you will. And so it's interesting that the copper is doing funny things, and yet the graphene just grows separate from it. And this is just a computer model. This is a paper we published with Jim Chesky in Nanoletters just a couple years ago. And at first we got some flack for it, but then everybody agreed that this seems to be what's going on. All right, I have another colleague, Kang Wang, in electrical engineering, and he likes to make things like memory devices. And so what we did is we took a silicon with an oxide coating. He had us grow CVD graphene on it, or transfer it. He then put a aluminum oxide coating. And between this, what we're doing is we're doing capacitive energy storage. So you can see these capacitance curves. On top is multi-layer graphene. Down here is single-layer graphene. And so you can actually store information on each of these little devices. And this is a paper from ACS Nano. People have been very interested in, could you grow 2 layers of graphene? Graphene doesn't have a band gap, but 2 layers will have a small band gap. And so we came at this from a chemical approach. Everybody's using methane. We asked the question, what would happen if you use ethane? And it's actually quite interesting. If you look at the Raman spectrum, if you use ethane at 250 millitorr, you get the traditional 1:4 ratio, which is single-layer graphene. If you do it at 1,000 millitorr, you get about a 1:1 ratio, which indicates bilayer graphene. And in fact, you can see this Raman map. This is perfect single-layer graphene. This is reasonably good bilayer graphene. But of course, you realize your eye can see it too. So if one layer attenuates 2.5% of visible light, 2 layers should do double that, right? So if you look here, here's what single-layer graphene looks like on the surface that we grew it, on the copper surface. Here's bilayer graphene. You can see it's darker. Or if you do the UV-vis spectroscopy and you go to 550 nanometers, you'll see that one attenuates a little over 97% of the light and the other a little over 94%. So you really can see the difference between monolayer and bilayer graphene.
What's the absorption feature at 300?
What's going on down here? I don't really know, because it's a very broad spectrum absorber. In fact, I'm going to show, we're going to hit it with a laser and watch it absorb light. So I don't, it's probably known because there's people who have studied these things, but I'll have to apologize. I don't really know. All right, so how are we going to scale this up? Because as I said, CVD is nice for electronic devices, but it's not particularly scalable. So graphite oxide's been known for 150 years. I can say that because here's a reference to Brody's work in 1860. Okay, and what is graphite oxide? Well, if you oxidize graphite with acids and strong oxidizing agents, you end up with a material that has carboxylic acid groups, it has epoxide groups, and it has OH groups. But what's nice about graphite oxide is it disperses completely in water as single sheets. So it's been known that it disperses in water. It's only till recently did people realize it's single sheets. So then the question is, if you have a single sheet of graphite oxide, can you get it back to graphene? Can you reduce it or deoxygenate it in some fashion? And so we've looked at this in great detail, and other people have too. And I'll talk about graphene paper. I won't bother you, but we've made a lot of field effect transistors. I'll mention something about sensors. I'll talk about graphite oxide foam, and then we'll look at Laser-scribed and how to make supercapacitors. Okay, first thing is, we hit it with hydrazine, a great reducing agent. And when you do that, you get the reduced graphite oxide, or graphene, and it disperses in water as single sheets. We know that it's a colloid, and we know it's a colloid and not a solution because it shows the Tyndall effect. The Tyndall effect is if you take a laser light, if it's a solution, the laser goes through it. But if it's little tiny particles, it scatters laser light. So you can see the laser light being scattered. We even know what kind of colloid it is. Every sheet of carbon has a negative charge, and so it stays apart from the other sheets. However, if you throw salt in, salt will neutralize the charge, and it will flocculate out. So we just call that the salt effect. And if you look by AFM, after you flocculate it out, you get these nice pieces of chemically reduced graphene. And if you run a probe along here, you can see that you get about a 1 nanometer step height. And so everybody in the field decided 1 nanometer is the step height of single layer graphene. The problem, of course, is in graphite, the inner layer spacing is 0.34 nanometers, 3.4 angstroms. So it's not clear that that is a single layer, but I'll show you we can do that. By the way, this is a paper we published with my colleague Gordon Wallace in Australia. My former postdoc Dan Lee went to Australia, and now he's a professor at Monash University. I was just there 2 weeks ago in both places. And anyway, we published this 6 years ago in Nature Nanotechnology. A year and a half ago, the editor-in-chief emailed me to say we had the most highly cited paper in the history of their journal. So it now has over 3,000 citations. So this is a fairly popular area to work in, as you might imagine. After we did this, we said, well, we can probably do better than hydrazine. In fact, hydrazine to us, N2H4, is what I call a green chemical. Why? Because at the end of the day, it goes away as nitrogen and hydrogen. Okay, some of you are laughing because if you know anything about hydrazine, it's incredibly flammable, it's explosive, it's used as a rocket fuel, and it's toxic. But it does go away as nitrogen and hydrogen, right? All right, so we said we can do better than aqueous hydrazine, which is what everybody else is doing. We said, what if we use anhydrous hydrazine? Now, I don't recommend this. We have a dry box with monitors set up to do this set of experiments. So you need to take some safety. But we took pure hydrazine, and we took our material, and it turns out it forms a nicer colloid, and even with pure hydrazine, just like it does in water. And we did this because we thought we could get rid of more of the. There's always a little bit of residual oxygen. We thought we could get down very nicely. So we did this as another paper from Nature Nanotech. And when we did this, at the time, we produced the largest pieces of chemically converted graphene that were known. In fact, they're so large that you can take an SEM picture and you can take an AFM picture, and I think that you'll agree that these are the same picture. We didn't use any alignment markers, so you can find these easily. And so I was getting funding from DARPA, the Defense Advanced Research Project Agency, and we're having a meeting at UCLA, and the program manager came and he said, I showed this, and he said, well, Rick, this is nice, but there's a problem. I'm like, what's the problem? He said, something's missing. I'm like, what's missing? He said, Florida, it's missing. Yes, so even program managers have a sense of humor, right? All right. But we can take this map and we can take a probe and go along white, go along red, and go along blue. And if you do this, you can see this little crack. We go over this. It's about 0.6 nanometers. Here's about 0.6 nanometers. Here's about 0.6 nanometers. So in fact, 2 layers of graphite are 0.7 nanometers apart. So this cannot be, this has to be a single layer. Then you can say, well, why isn't it 0.34 nanometers? Well, there's been a lot of debate as to why that is. But the simple answer is probably we're just doing this on a silicon surface with an oxide. It's not flat. Now, it could be there's a little residual oxygen. There could be hydrogen. There's all sorts of possibilities. A better experiment would do if we did this on freshly cleaved mica. But none of my students want to go back and do that because, it's somewhere. But at least we can demonstrate, even by AFM, that it is a single layer. Okay. Once you've made this, and you can scale this up. With aqueous hydrazine, you can make as much as you want. So we've made beaker loads of this stuff. We'll take plastic filter paper and we'll just filter it through. And all these layers gather together and they stick together. And we peel it off the paper, we make freestanding graphene paper. And so this is completely flexible, and you can see your shadow in this. And this is a paper from Science a few years ago. And at the same time, Rod Ruoff published a paper in Nature and showed that this stuff actually has fairly high tensile strength. But it's easy to make this into objects, if you like. Once we had graphene, we wanted to know, how do we move it from place to place? So our first thought was, let's just make a stamp. So we took polydimethylsiloxane, and here's a block of this rubbery plastic. And we took one that was missing, one of these spikes was broken. So it's a stamp with 3.5 plates. Okay, so we ink the plate with graphene, we pick it up, and then we carefully move it on and we stamp it over here. Now, of course, there's some problems, and one of the problems is we have to heat it to 85 degrees, and it takes about 2 hours to transfer the stamp. But we were able to transfer it. So you can stamp graphite here and move it there. This isn't a very attractive process. And we suddenly realized that graphene actually doesn't like PDMS. And that gave us a simpler idea. And the idea was this: what if we just make a PDMS stamp? Okay, and what we did, in this case, we just took PDMS and we drilled holes in it. Well, how did we do that? We took silicon and made a platen. We poured the PDMS on top, and when it dried, it left all these little holes. And you can see the holes. That's the oxide of silicon through the holes. And you can look at this edge-on view, you get these nice holes. Okay, there they are. And then we take that PDMS and we can put it on any surface we want, and it will leave residual PDMS. And then we spin coat the graphite oxide. And when we do that, or the reduced graphite oxide, when we do that, it will only go where the PDMS is not. And so by doing that, here we spelled out UCLA in chemically reduced graphene. And you can make electrodes, you can make anything you want. So we think this is a good way of depositing graphene where you want it. Okay, we then thought of, what if you could you combine chemically reduced graphite oxide with carbon nanotubes? And so we tried this with pure hydrazine, and this is in collaboration with my colleague Yang, who many of you know. And just to show you, here's pure hydrazine with, we have slightly oxidized carbon nanotubes and our graphene material, and this is chlorobenzene. And an hour later, you'll see hydrazine, everything stays as a colloid, things start precipitating out of chlorobenzene. And this is, the hydrazine is very nicely stable. Okay. When we did this, the reason we were interested in this is to make some transparent conducting electrodes. And so what we did is we used different spin speeds, and you'll see the faster you spin this stuff on, the thinner the coating of carbon nanotube graphene that you get. And you can physically see this. And you can put this on any surface. So here's sapphire, here's plastic, here's silicon. Okay, we are particularly interested in what happens on plastic. And so what I'm showing you is a current voltage curve. And of course, indium tin oxide is the conducting transparent material used on all your cell phones and electronic devices. But of course, there's not enough indium in the world to, if we someday put solar cells in everybody's house, that's going to be a problem. And so people are looking for a replacement. And there's another problem with indium tin oxide. It's a nice crystalline inorganic solid. So in fact, what we're doing is we take ITO, indium tin oxide, and we put it on plastic. Okay? We take our graphene and carbon nanotube mixture and we put that on plastic, and we get to the same conductivity. We then bend each of them 10 times. The crystalline inorganic ITO loses 3 orders of magnitude in conductivity. But our molecular material, you can bend it as much as you want. It's molecular. Nothing happens. So it's still as conducting as before. So all this tells you is carbon nanotubes, graphene, anything made out of carbon, you can make flexible electronics. So that's good. Now, whether that's good enough to make transparent conductors is, we can debate that. I had the opportunity about a little over 2 years ago to be a co-guest editor of MRS Bulletin, devoted to making conducting transparent electrodes. And so I'll pass this around because there's one interesting thing. The cover is, we were asked to design the cover. So I asked my students, and one of my students was actually an artist as well as being a scientist. So he designs the cover, and you'll see the sun, sending light onto graphene. And after this came out, my other student said, oh, you know that Jonathan Wassé signed the cover. like, what are you talking about? And sure enough, under where the wording is, if you look carefully, his name appears there. I didn't see it, neither did the editors, obviously. But after I pointed this out, people were like, oh, maybe we should offer him a job. So anyway, he just got a job in the Bay Area. He works for a startup company that makes transparent conducting windows, amazingly enough, in roll-to-roll processing. Okay. Shifting gears slightly, sensors. This is a micro hot plate sensor, and this is done by, I have a colleague at Aerospace Corporation. It's a nonprofit FFRDC. They do a lot of Air Force contracts. They're near LAX airport if you've been there. And they have 1,400 PhD scientists. They're a national lab that nobody knows about. But in their spare time, they can do whatever they want. So my friend Bruce Weiler makes micro hot plate sensors. So he asked me if we could put some graphene on one of his micro hot plates for sensors. And so here's a little piece of graphene that we put between two interdigitated electrodes. Okay. If we look at the band structure of graphene, so here's the ground state of graphene. The pi states form a filled valence band. The pi star states form an empty conduction band. So in principle, if you n-doped it, you'd add electron density to the conduction band and become more conductive. If you p-doped it, you'd pull electron density from the valence band and become more conductive. So this is not a good material to make sensors out of. Okay. However, the material we use, we start from graphite oxide, and it's partially oxidized. There's always a little bit of residual oxygen. So here's the band structure we believe we start with, right? We have some holes in the valence band. So if we bring up an electron donor, ammonia is a good electron donor, at 5 parts per million, every time it sees ammonia, the resistance goes up. Okay, why is that? Well, if you think about it, what we're doing is we're filling in states in the valence band. So we can detect ammonia at 5 parts per million, no problem. Okay, if that's true, then if we withdrew electrons, we should see the inverse effect, and here it is. So here's NO2, electron withdrawing, 5 parts per million. Every time it sees the NO2, the resistance drops, so it becomes more conductive. Why is that? Because in this case, we're further p-doping it, so we're removing states from the valence band, so it becomes more conductive. Now, I know some of you work on sensors, and you're probably looking at this and said, this is the worst sensor I've ever seen, right? We have a drifting baseline. It's not completely reversible. Okay, fine. This is why we're using micro hot plates. We can fix these problems. At least Bruce Weiler can. So what he did is he just heated it up to 150 degrees, and all of a sudden, this is, NO2 at 5 parts per million. It's completely reversible. Okay, so you get a very nice looking sensor. Then you might say, well, why should I even care about NO2 or even ammonia? So, okay, I'll give you something you can care about. So this is 2,4-dinitrotoluene at 52 parts per billion. And you can see we have pretty reasonable signal to noise. Okay, why should you care about this? Well, if you think about the explosives in the world, trinitrotoluene, it turns out the volatile component in TNT is dinitrotoluene. And the vapor pressure is about 700 parts per billion. So if you can detect this at 50 parts per billion, you can actually use this for explosive detection. So it's actually possible to think of this as a sensor material. All right. Now I want to show you something else. We're going to take graphite oxide and we're going to freeze dry it. So we get a nice golden color solid. We're going to expose it to light and we're going to do some conversion. And this idea came from work in my lab on conducting polymers. And Zhejing Wang was one of my students. He just got tenure at Northwestern. And after he went to Northwestern, he had the same idea that we did. And he published in JACS a couple months before our Advanced Materials article came out. But I want to show you what happens. And so before I show you how to control this reaction, I'm just going to light graphite oxide on fire, just an ordinary lighter. It's kind of fun. If I can find the pointer. Now, I'm going to expose it to a camera flash. So this is graphite oxide paper. Okay, so what are we looking at? Completely uncontrolled reactions, right? What's going on here, amazingly enough, it looks like it's burning, but it's essentially deoxygenating. So it's getting hot and giving off CO2. It turns out that we believe this process is exactly the same. It's absorbing the light, converting it to heat, and blowing off CO2. And when we're done at the end of the day, we can actually control this using a technology called Laser-scribed. So let me show you what that looks like. Some of the younger people here probably know. Some of the older people like myself need to be introduced to this. So Laser-scribed is a DVD burner. It costs about 25 or 30 bucks. You can order these on the internet. And they use the Gillette razor model. What's the Gillette razor model? Give away the razor, charge for the blade. So they give away these devices pretty much at cost, and they charge you for the light-scribed enabled disk. So what does this do? Well, it's a process for labeling CD disks. So you can put your initials on a CD or some other figure. And the idea is you have a 780 nanometer laser and a magnifying glass and a very sophisticated computer program that you can take any digital image and raster it. And so you can take this laser and you can draw on this. Now, of course, we don't like to pay for a lot of CD disks. So one of the things we did is we simply put a piece of plastic down, put our graphite oxide on the plastic, and hit it with a laser. And what we found out, here's a current voltage curve. So graphite oxide, of course, is insulating. But as soon as you hit it with a laser and it becomes graphene, it becomes conductive. And what does this look like? Here's what it looks like. So here's a piece of plastic, just polyethylene terephthalate. And the golden brown colored material is the graphite oxide that we just put on. And then when we hit it with a laser, we can draw anything from interdigitated electrodes to nice looking figures. Now I said we first did this with conducting polymers. So I'm going to pass around a couple of these things so you can see for yourself what I'm talking about. So the first one I'll talk about is another area that I work on, as you heard, is conducting polymers. And the problem with conducting polymers, I worked on the first one, polyacetylene, which won the Nobel Prize for Alan Heeger and Alan McDermott. And the problem with conducting polymers is unlike other polymers, you know, if you look around you, the chair you're sitting on, the carpet, your clothes, they're all polymers. Yet you probably would be hard-pressed to name an application for conducting polymers. Some of you might because there's a lot of work out here. But most people can't. And the problem is that the reason everything's polymers around us is two reasons. One is polymers are cheap, but the other thing is they're processable. You can melt them, you know, and make objects out of them, or you can dissolve them and coat them. Conducting polymers don't do either. So a number of years ago, about 15 years ago, we set out to make nanoforms of conducting polymers. And it turns out when we make nanofibers of polyaniline or any other ones, they disperse in water. So we put them on a CD disk, we hit them with a laser, and they actually melt. So we know how to process them in water, we know how to melt them. So here's the UCLA logo printed in polyaniline. 3 years ago, I was fortunate enough to win the Tolman Medal. And Tolman is a Caltech professor. It's the Southern California American Chemical Society Award. And so my students for the occasion looked up Tolman. And there's a famous picture of Tolman on the internet. Now Tolman's the first to explain how copper conducted electricity. So I liked that. I thought, okay, I work in this area of conductors. And so I'll pass this around. Hopefully you'll be able to see this. There's a picture of Tolman made in polyaniline. My students did this for that occasion. Tolman's the guy you don't recognize. You'll recognize the other guy. And you'll find out what theory Tolman actually worked on. And then my favorite picture of all is this one. Ah, good. So there's a little bit of lighting. And what this is now we're going to graphite oxide. So with conducting polymers, they go from conducting, they melt, they become insulating. But with graphite oxide, it's insulating. We hit it with a laser, it blows, it gets hot, blows off CO2, and turns into a form of graphene, becomes conductive. So here we're actually drawing conductive lines. And my students have this interesting sense of humor, so they drew graphene out of graphene. And of course, you can make images. So here's one of the first images we made. We paid an artist for this picture of a person with a computer for a brain, and we reproduced this in laser-scribed graphene. And so what this is the dark places, we just told the laser to hit it and completely convert it to graphene. The light places the laser didn't hit, and the grayscale in between is partially deoxygenated. Okay, and there's a paper from ACS Nano not that long ago. Now, we also can print interdigitated electrodes. So here's the graphite oxide on plastic, and we print a bunch of interdigitated electrodes. And we ran, in this case, this is NO2, and you'll recognize this at room temperature. You get this nice response, but a drifting baseline. Okay, so you can make sensors and other electronic devices. The most interesting thing is I have a student, and you'll meet him because I'll show you a movie with him in a little bit. And he came from Egypt, Maher El-Kadi. And I met his advisor through an internet hookup. And his advisor is the head of the science at Cairo University. He was the dean of the faculty of science. And we went around and said what we did. He said, oh, I work on conducting polymers. And I'm like, oh, I work on conducting polymers. Then he said, well, the best student I've ever had is about to finish his master's degree in electrochemistry. And he needs to do a PhD. He's got a position at Cairo University, but he could do it in my lab or he could do it in yours. And I'm like, who would pay for it? He said, oh, he's so good, I'm sure the Egyptian government will. I said, okay. So 50 emails later, Maher comes to my lab, and I was on his thesis committee for a master's degree. And so he immediately takes our chemically reduced graphite oxide, and he runs a cyclic voltammetry experiment. And what he does is he put in the iron 3, iron 2 couple, ferrocyanide. And he comes back to me and he said, the peak separation is 0.059 volts. And I said, I don't think so. He's like, what do you mean? I said, look, I studied electrochemistry, and I know from the Nernst equation that the theoretical limit, maybe I learned this from Professor Estrup's class back at Brown University, but I know the theoretical limit is 0.059 volts, and it's a kinetic experiment, so you can't get that. He said, you're wrong. He said, the Nernst equation is here, and the theoretical limit is 0.05916 volts. And when I measured the peak separation, I got 0.0595 volts. It's legitimate. But that's amazing, right? It means this is really good redox active surface. And so you can calculate the speed of electron transfer. And so Maher did that, and it turns out on laser-scribed graphene, the speed for electron transfer is 10 to the minus 2 centimeters per second. Now contrast that with graphite. Graphite is the electrode material of choice for almost all batteries and electrochemical devices. The speed for electron transfer is 10 to the minus 4 centimeters per second. So we have a material that's 100 times faster for doing electron transfer than graphite. So it immediately became obvious that we should be doing energy storage. And so that's what I'm going to show you next. Actually, I'll show you one other experiment before I do that. Another thing you can do is you have this surface. You can set up a electrochemical cell, and you can deposit whatever metal you like. So if we take a platinum 2 salt, we can reduce it to platinum 0. So here's nanoparticles of platinum, nanoparticles of gold, nanoparticles of palladium. And after 2.5 minutes using a palladium salt, we get 10 nanometer particles, quite uniformly dispersed. If we let this run a little longer, this is 7.5 minutes, they grow up to 12 nanometers. If we let this go for 20 minutes, we're up to 17 nanometers. You can grow whatever size particles you want. And this could be useful for sensors and maybe catalysis or something. Okay, but let me talk about energy, because that's why I'm here. Okay, we all know that there's a problem with energy. You can make the world's best solar cells, but the sun doesn't shine all day, so you need something to store it. The wind doesn't blow all the time, you need to store it. Your computer and your cell phone, they're always not quite charged when you need them. So it'd be nice if you had better ways of storing energy. And if your worst problem is that your Tesla doesn't make it all the way from Northern California to Southern California without stopping for a long lunch, then maybe we can solve that too. Okay. So here's a common problem we all encounter, right? And my student took this picture off the internet. It's infuriating sometimes. Now, let's talk about the difference between power and energy. So energy is how much you can store, and power is how fast you can deliver that energy. And this is taken off of Maxwell Technologies' website. They're the leading supercap company. They happen to be located in San Diego. So a capacitor supplies high power but low energy. A battery provides high energy but low power. And so what we're after is something that combines the best of both, hopefully, and that's called a supercapacitor. And a supercapacitor is going to look like a battery, but it's fundamentally different. So let me first make sure everybody understands this. So a battery, of course, has an anode and a cathode, an electrolyte, and a separator. If you have a lithium-ion battery, what do? You insert lithium into one electrode and some electrolyte, it expands. You pull that out, it contracts. You do that 1,000 times and you've lost a lot of capacity. Why? Because some of that electrode material gets inactivated. Okay, it's no longer accessible. So that's why our cell phones and our computers, after a couple years, you need to replace the battery. Supercapacitor looks similar. It has a positive electrode, a negative electrode, often a separator and electrolyte, but it works on a fundamentally different principle. The idea is that each of the electrodes has exceedingly high surface area. There's electrolyte ions next to each of the electrodes. When you charge it, the one set of ions jumps onto one electrode, the other set jumps onto the other. And they only move atomic distances. When you discharge it, it goes the other way around. There is no expansion, no contraction. So supercapacitor electrodes can last millions of cycles. And so they're used very differently. Of course, they don't store as much energy, but they've got that potential. Okay, where are supercapacitors used? Well, they're already used backup power. Here's for cities, for buildings. They're used in windmills because they have very reasonably fast time responses. So as the wind changes, they can be used to change the direction of the windmill. And they're used in cranes on ports. It turns out if you go to Japan today, all their ports are using supercapacitors because when you load that thing on a ship, you know, when you pick it up, it takes a lot of energy. When you drop it back down, if you have a supercapacitor, you can recover 40% of the energy. Battery can't do that because the time constant takes too long. So supercapacitors going in, the ports in LA and Long Beach will have to do this soon because it's basically free energy once you pay for the infrastructure. And what may surprise you is you may actually have a carbon-based supercap in your pocket. So carbon-based supercaps now comprise, it's a billion-dollar industry. It didn't exist 20 years ago. But you might have one in your pocket. So this is something produced by CapX in Australia. And you can see what this is. This is the energy source that's the flash to a cell phone camera. And this is shown a standard battery-powered flash. And here's one powered by a carbon-based supercap. So it's a very, very powerful burst of energy. And as I said, you might have one in your pocket. A very neat use is electric buses. So if you go to China today, there's a new fleet of electric buses where the charging station is the bus stop. So as people get on and off the bus, within about 2 minutes you can charge this bus. Now what's nice about this is not only is it clean because it's an electric vehicle, but you don't need much infrastructure. So you need to connect a bus stop every 5 or 10 miles to the grid. And that will be a charging station. The rest of the bus stops, it doesn't matter. And this bus can go 24/7, 365 days a year for years on end, just using these carbon-based supercaps. So in fact, Maxwell Technologies sells a lot into this market. This is my favorite application of all. This is a train station in Amsterdam. Yes, and this revolving door is connected to a supercapacitor that's running the lights in this restaurant. So this is human-powered energy. So this is where we're all headed. All right. If you look at energy, you want to think about a Ragone plot. And it's power density in watts per kilogram versus energy density in watt-hours per kilogram. Capacitors have very high power, very low energy. Lithium-ion batteries have very high energy and relatively low power. So what we want is something that bridges the gap between these, a supercapacitor. In fact, the Department of Energy has a goal for electric vehicles, and here's the goal. And what I'll show you is that not only in theory can graphene by itself pass this, but we actually have lab models that actually are beyond the goal. Okay, now it turns out the theoretical specific capacitance of graphene is fairly high. It's 550 farads per gram. The problem is that's assuming you can use every surface. In practice, what people only get is about 100 to 150 farads per gram. And the problem is that carbon in the form of graphene likes to restack. And the theoretical surface area of a sheet of carbon is 2,630 meters squared per gram. But imagine if you take a second sheet and put it on top of the first. You lose half the surface area, right? Half the bottom and half the top. So you're down to 1,300 meters squared per gram. So all of a sudden you've got a problem. So the trick is, how are you going to keep the graphene sheets apart? Well, I'll show you that our laser-scribed graphene does that. We didn't start out to do it. It just happens to be the structure we got. But when we measure our surface area, we're measuring above 1,500 meters squared per gram. So we're activating more than half of all the surfaces. Okay, how do we do this? We take a DVD disc, we put a piece of plastic on it, we coat it with graphite oxide, the golden brown material. In this case, we tell the laser to darken the entire material, turn it all into graphene. We then cut 2 pieces of plastic. So we have our graphene here, we put in a separator, an electrolyte, and graphene there. And I'll pass these around so you can see what they look like. In fact, I've got some electronic devices here. You You can take a look at these. And then I have some supercapacitors, and you can pull these out and play with them. They're completely flexible. One of these has a separator. You'll see a white ridge around it. The other doesn't. It turns out that it's actually hard to short these. You'd have to put a lot of pressure on, even without the separator. With the separator, you couldn't short it unless you punctured it. But anyway, that's simply how we make our energy storage devices. And here's what they look like. That's what's going around, a little pouch cell. Okay, this is the key to the whole thing. We told the computer to simply draw stripes of laser-scribed graphene with non-laser-scribed graphene. So the laser-scribed graphene is going to be the dark part. The graphite oxide is going to be the light part. And if we look at this under a microscope, graphite oxide is this beautiful layered compound. After we hit it with a laser, it absorbs the light, converts it to heat, and blows off carbon dioxide. What we're left with is this corrugated cardboard type structure, which when we put an electrolyte in will essentially touch every surface. And it's very highly conducting, very high surface area. It's exactly what you want in a supercapacitor electrode. In fact, when I was in Neil Bartlett's lab in the mid-1980s, 1984 to 86, he told us he had a dream. And his dream was to make something he called holy graphite. Holy spelled H-O-L-E-Y. He said graphite is the world's best electrode material. It's cheap, you pull it out of the ground. It's highly conductive, but it has one drawback, low surface area. So his dream was to drill three-dimensional holes on the atomic scale to make it high surface area. So I had the opportunity a year ago to give the Neil Bartlett, unfortunately it's a memorial lecture. So he passed away about 5 years ago. And so I talked about his dream of making holy graphite, and I said, okay, here's our version of holy graphite. And afterwards, I was very surprised. I had dinner with 5 faculty members who I knew from my time there, and a member of his family. And all of them said, oh yeah, Neil Bartlett used to always talk about his dream of holy graphite, which shocked me because, as you guys know, professors often talk about their dream with their own students, but they seldom talk about it with everybody else because either A, people will steal it if it's a good idea, or they'll laugh if it's a crazy idea. But here he was. So it's my only regret is that he's not around to see that we can do this. Okay, now what does Maxwell and these other companies use? Maxwell sold over $200 million of carbon-based supercapacitors last year to go into buses, to go into backup power for trucks. They use activated carbon. Here's what activated carbon looks like. Here's what our laser-scribed graphene looks like. The nice thing is we have a conducting material. It's in the form of an electrode. We can use it directly. And I'll just tell you, it's flexible, it has high surface area, and it's highly conductive. Okay, it's completely flexible. And I can say that because if we look at the change in resistance as a function of curvature, if you bend it, actually the resistance goes down a little. If you let it go, it goes back. In fact, you can do this 1,000 times, and here's the change in resistance after 1,000 bends, no change. So it's completely flexible, no loss. Okay, so you can make flexible electronics. Here's what the cyclovoltammetry looks like, current versus potential. What we're after here is if you want pure capacitance, the textbook says you would get a rectangular wave. Well, this is as close as you're probably ever going to see to a perfect rectangular wave. And so it's a pure capacitance type reaction. We can compare this. Here's what our structure looks like. So as I said, just our active material on plastic, electrolyte, separator, and same thing here. This is what a commercial supercap looks like. You can buy these. And here's the stack capacitance in farads per cubic centimeter versus current density in milliamps per cubic centimeter. At low current, we're comparing ours to the commercial thing. They both have about the same properties. But as you drive the commercial one harder, it falls off. And ours is still performing. Here's at 5,000 milliamps per cubic centimeter. I'll show you, you can go much higher with these if you like. So these are very high power devices. Okay. We're looking at the phase angle versus frequency because we want to know how fast they respond because this is important for various applications. And so it turns out that a commercial supercap, carbon-based, has a time constant of about 10,000 milliseconds. Whereas our material has a time constant of 30 milliseconds. You can compare that to an aluminum electrolytic capacitor as 1 millisecond. So we're not quite as fast as these aluminum capacitors, but realize that aluminum capacitors don't store any energy. They're just very fast. And so you can think of using these for applications. It simply means If you multiply this by 4, you can figure out how fast you could charge one of these energy storage devices. So in much less than a second, you could completely charge a device if you so desired. Okay. Now, as I said, these are completely flexible. This is a cyclic voltammogram, and we're doing this as a function of bending angle. So we literally bent this, and we're doing the electrochemical experiment. You'll notice that every curve is on top of every other. So it doesn't care if it's bent. In fact, for fun, my students said, well, let's just light an LED with a flexible supercapacitor and show people what this looks like. Okay, so I'll just click on this. And you'll see we're lighting this LED, and now we're going to bend this supercapacitor. And if you watch the LED, absolutely nothing happens. We also, for fun, put a piece of graphene in line as a conductor, and they're going to bend that in a moment. And if you look at the LED, you can bend the electrodes, and again, nothing happens. Okay, so all this shows is graphene is a good conductor, it's a good charge storage device, and you can use it to do real work. Now, if you look at your computer, it's not based on 1 volt of an aqueous cell or 3 volts of a acetonitrile-based cell. But in fact, it operates at 14.4 volts and about 4,400 milliamp hours. So how are you even going to get to 14 volts? Well, what you're going to have to do is you're going to have to put cells together in series. And so here's a 1 volt aqueous cell. We put 4 of these together in series, and you'll see we get out 4 times the voltage. If we put 2 in series and 2 in parallel, we double the voltage. Now we're going from 1 to 2 volts. And we double the area under the curve. So one of the things this tells you is the internal resistance of these cells is very, very low. In fact, if you look at charge-discharge curves, if there's an internal resistance, you get an IR drop right here. And it's very hard to see much of an IR drop. So we have very low internal resistance cells. So you can stack these and get whatever voltage you want. You can up the current. Here's the cycle life. So we're running this 10,000 cycles, because that's all we decided we have time for. And you'll see the capacitance retention is very good after 10,000 cycles. The shelf life is quite good. We ran this for 4 months, and you can see it's quite stable. So it has the right characteristics for a supercapacitor. And as I said, if you use an aqueous, you get 1 volt. If you use acetonitrile, you can get 3 volts. And if you use an ion liquid, you can go to 4 volts. And I should tell you, we're now up to about 300 farads per gram with the acetonitrile-based cells. Okay, if we put this on a Ragone plot, power density versus energy density, here are commercial supercaps, here are caps, capacitors, here are lithium-ion batteries, here's our material. This is our aqueous materials, our organic-based materials, ionic liquid-based materials. So we have stuff that certainly is competitive with lead-acid batteries. Of course, its power density is a factor of about 1,000 greater. And as we get into ionic liquids, we start to approach the energy density of lithium-ion batteries. We still have a ways to go. In fact, nobody's claiming that you're going to replace supercapacitors with batteries anytime soon. But there's a lot of work on putting them together where the batteries provide the high power. The supercapacitors provide the high power, the batteries provide the high energy. And so you'll see hybrid systems coming out commercially in the next couple of years. Now, I want to talk a little bit about micro-supercaps, because I think this is also an important area. And we all know about Moore's law, so I won't tell you anything about Moore's law, but one of my students said, what if Moore's law applied to batteries? Okay, how big would your car lead-acid battery be? And the answer is the size of a red blood cell. So clearly Moore's law doesn't apply to batteries, and it never will. There's no scaling law of batteries. In fact, batteries in the same time that Moore's law has applied to semiconductors have only doubled in energy storage. And they improve, but they don't improve that much. So it would be neat if you could make some breakthrough in energy storage. And in fact, another problem is if you look at any circuit boards, what takes up the most real estate? It's the capacitors. And what dies when your boards die? It's the capacitors. So it would be nice if you could have better capacitors, better line filters. And that is possible, potentially, with supercapacitors. And even what takes up the most real estate in your cell phone? It's the battery, the lithium-ion battery. So it'd be nice if one could make an improvement. Okay, so we started looking into what I'll call micro-supercaps. And these are things that, you can think of little batteries to run pacemakers, radio frequency devices, MEMS sensors, hearing aids. And so the main competition here are little tiny lithium microbatteries. And then there are micro-supercap designs. So we just said, let's take one of these designs because they're interdigitated electrodes. And can we do this with our material? Well, of course, we can print over 100 micro-supercaps on a single CD. And if you blow this up, what we're doing is we're drawing interdigitated lines. And so we can make electrodes that are very close together. So basically, this is going to be electrode A, this hand, and this hand will be electrode B. And we'll just connect this. We'll put a drop of electrolyte. Now, the difference between this and a macro supercap is if you think about it, a macro supercap is you have an electrode here, here's your material, right? Here's a separator. And so you have some, resistance due to the electrolyte there. But if you have a micro supercap, you can put these things much closer together. You're moving ions this way. They're closer together, less resistance. So you can get really high-powered devices. And so here's what this looks like. This is 4 interdigitated electrodes, 8 interdigitated electrodes, and 16. Here you can see a picture of what these look like. And if we look at the capacitance, here's our macro device, and here's our micro device. And so you can see you can store a lot more material. And if you look at the charge-discharge curves, they're quite nice. There's just a very tiny IR drop. And now if you look at capacitance versus current density, we're running this out to 20,000 milliamps per cubic centimeter. So the equivalent of 20 amps you're running through this, and it doesn't bother it. Of course, the commercial stuff doesn't like that. Okay, and you can put this on a Ragone plot. We've reversed this now, power density versus energy density. The take-home message here is that if you look at lithium-ion thin-film batteries, and you compare it to our material in ionic liquids, and by the way, we gel all our materials so they don't leak. So in other words, if we use aqueous stuff, we'll put in polyvinyl alcohol so it won't leak. If we use ionic liquids, we'll put in a little of silica so you make a gel. And one of the things I don't understand, I think all battery manufacturers should put in a drop of these things in so batteries don't leak, not ruin your electronics. It wouldn't cost hardly anything, but maybe a fraction of a penny is too much. I don't know. Anyway, if you look at power density versus energy density, we are now competitive with thin-film lithium-ion batteries. So you can make these little tiny storage devices that have high power, but the energy is comparable to lithium-ion batteries. Okay, with that, let me say that hopefully I've convinced you it's possible to make graphene. CVD is good for electronic devices. Chemically converted is what's going to be needed for other things. Transparent conducting electrodes are possible. I like laser scribing because you can control where you put it. You can make high-performance supercapacitors, and you make as many micro-supercapacitors as you like. And if you're interested in more information in general on graphene, Jonathan wrote an article for Council of Chemical Research last year, and it was the most downloaded article when it came out, probably because of his sense of humor. It's called "Oh, the Places You'll Go with Graphene." Okay, and last year a filmmaker came to me and he wanted to make a film for Sundance Film Festival. It was a short 3-minute video on ideas that would change the world. When it made he promised he would make the top 100 films. When he made the top 20 films finalists, he said, okay, get ready, we're going to go to Sundance. But it didn't win, although it was released to the internet and went viral, over 2 million views within a couple months. So I want to show you that next. A lot of times, experiments in science or discoveries look like accidents. But they're only accidents in the sense that we were trying to find something else, and then we realized that what we had was better for a different application. Graphene is a single-layer carbon. It's one of the strongest materials ever known, and it's completely flexible. The discoverers of graphene won the Nobel Prize in 2010. However, the method they used to make it, which was taking graphite and peeling it with Scotch tape, is not practical. So we set out to find a better method. We start with graphite oxide, which is a water-dispersible material. We then coat it onto sheets of plastic. We hit it with a light from a laser. Deoxygenates, it turns it into graphene.
So it's both very exciting because we made all organic graphene in a very simple process using consumer-grade B2B drive that you can find everywhere.
But the real discovery was yet to come. I think the eureka moment that you're looking for was not exactly that. The real exciting discovery came when Maher dragged me into the lab. And he said, take a look at this. And he just took a light bulb and he just turned it on with this little piece of graphene. But the amazing thing is, it doesn't stop working. After charging for 2 or 3 seconds, he ran this light for over 5 minutes. supercapacitors you can think of as a charge storage device like a battery, except it charges and discharges 100 to 1,000 times faster. A battery stores a fair amount of charge, but it charges and discharges slowly. A capacitor puts out a high output, but it doesn't store much charge. So like the flash to a camera, a supercapacitor is one which combines the best attributes of both. If you think about all the electronic devices you have, right now, every time you need one, you realize, oh, I forgot to charge it up. But imagine if you could take that same device, plug it in the wall for 30 seconds or a minute, and be ready to go. Life would be very different. And eventually we'll get to things like electric vehicles. Now you pull into a gas station. Well, you pull into a charging station, and within a minute, it would charge up your car. If you think of batteries are all composed of a lot of metals. Often they're toxic metals. And so, in fact, you're not allowed to throw a battery away. But if you had something that's carbon-based, it wouldn't matter. Carbon-based, you could put it in your compost bin and use it to grow vegetables. When I was a kid, I wanted to be a scientist. And so my goal has always been to develop something that will change people's lives. Okay, with that, let me thank my students who have done all this. You met Maher. He just finished his PhD, and after a few months in Egypt, he's come back to join me as a postdoc. Sergey's done a lot of work. In fact, he was sponsored for a couple of years by the Mitsubishi Center for looking at graphene for doing gas barrier work. Jaime Torres, Lisa Wang have worked on these. Veronica actually did the original Laser-scribed work. She now works at Intel. Jonathan you met, he works at this startup company, Rolith Incorporated in the Bay Area. Scott went on to Northrop Grumman, Matt to McKinsey and Company, and Vincent, who is a joint student with Yang Yang, is at UC Merced. And I'd like to thank all our sponsors, which includes Maxwell Technologies. And I'd like to thank you for the invitation and for your attention. Oh, thanks.
Technically,
Yes.
the laser-scribed graphite,
Yes.
graphene, is not really, right?
That's right. That's right. So the definition, what he's alluding to, as you know, the definition of graphene is a single layer. And of course, what we're doing, if you're going to make a practical device, you can't use one layer. You need hundreds of layers. And at the end, we've taken hundreds of layers and knit them together by the penetration depth of the light, which is actually knitting these together. So you're right. I call it graphene. Why? Because graphene is popular. It gets people's attention. But of course, what we have is a three-dimensional form of carbon. You can call it a carbon foam. You can call it a corrugated carbon structure. In fact, we've had some people who are interested in investing, and so they looked into our patents, and they did a patent analysis. And they were very pleased because it turns out the field of graphene and supercapacitors is a crowded field. And they were very happy they found no mention of graphene in our patent applications. Interesting. So, yes, you're right.
Just an epilogue to that. Do you remember Eduardo Falcao?
Yeah, sure.
Well, he made exactly the same kind of structures by adding sodium or lithium
Yep.
to hot
Yep.
hexachlorocyclopentadiene. And the dechlorination is so explosive. I mean, we have movies on that. And the residue looks...
We should probably test it because it may be similar in nature. It depends on the size and so on. Yeah, the student he alluded to got his PhD with Fred at UCLA. He came in my lab and did a number of experiments. So Fred and I have a very nice paper in the journal Carbon together.
What line width did you get in laser scribing technique?
Yeah, good question. So these cheap lasers are 780 nanometers. And so you may ask, what line do they draw? Well, they literally draw a 780 nanometer line. Now, there is some thermal spread. So then the question is, can you use other wavelengths of light? And the answer is yes. In fact, you can use, the green laser I'm using, you can use this with one caveat. And that is you need to take a magnifying glass because you need to focus the power. So there's a minimum amount of power. It's about 2 milliwatts of focused power. In fact, when I was in Australia a week and a half ago and talked about this, they said, how powerful is that green laser you're using? I said, well, it's a 5 milliwatt laser. They said, ooh, you're not allowed to have this in Australia because apparently it's, so I'm like, okay, I didn't know. But then the question is, can you go down? And the answer is yes, but there has to be a limit because there's some thermal spread on this, and I don't know exactly what it is. We got a hold of a laser box. We've tried different colors, so the normal range is fine. But I've done, excuse me, a collaboration with a group at the Kennedy Space Center because they wanted to ask that question. What if you took? They said we have one of the world's most powerful lasers, and of course, if you take too much power, the first thing we told them that you're probably just going to blow it away. Well, they blew it away, but then they started attenuating their laser power, and then they said, okay, now we've got it. We can. So I don't think it matters what wavelength you use unless you want to draw fine lines, but it is the focused laser power that makes all the difference.
Just want to make tiny sensors. I'm just thinking something simple. Use like a Blu-ray, which
Yes.
is roughly 2 to 3 times smaller.
Yep.
Yep.
So, yeah, in fact, it turns out that the manufacturers are very clever on these devices. And we spent a long time trying to use the same Blu-ray technology with the Laser-scribed. And it can be done, but it's not easy to do. I mean, somebody who knows electronics could probably do it. But you can use the blue laser. But I just don't know how to connect it to the Laser-scribed. We wasted a lot. We even sent it away to some electronics firm who promised they would get it to work for us, but they never did. But I think you could do that, sure. And I think that would be a neat idea. You could draw little tiny devices. If you're interested, great. Yeah, this whole process, it looks so simple that after this movie came out, I started getting emails from high school students. I want to do this. And I would say, well, I don't think you do, because graphite oxide in theory is cheap, but if you try to buy it, the suppliers are charging a fortune for it, so it gets expensive. And then finally, 2 high school students wrote to me, and they said, take a look at the pictures, we did it. So I stopped discouraging high school students. Then a month ago, a homeschool group, so now we're talking grade school kids, but led by some parent, emailed me and they said, we're going to do this Laser-scribed. So I sent the same thing. I said, here's our papers. I really don't have time to help you with this project. And then they wrote back to me and said, okay, we got the laser-scribing to work. Now we want to make supercapacitors. And they wrote to me and they said the supercapacitors don't work. They put 2 electrodes together. And so I wrote to them. I said, well, what electrolyte did you use? And they said, what's an electrolyte? So I told them to put in some acid that they could get. So they got some sulfuric acid. They put it in. They wrote back, it's working. So anyway, it's possible.
I should mention that Rick has done many things in other areas too. He's made super hard thermoelectrics, for example, high temperature thermoelectrics, which are quite interesting as well.
Yeah, and in another project, we've made the world's hardest metals, and we're trying to. Yeah, we've done some thermoelectrics, but you've probably done, yeah. So, I'm sorry, the edge of the graphite? Oh, what's around, like graphite oxide, when you convert it, what's around the edge? Is that the... Mm-hmm. Yes. Yes. So people have debated for a long time what the edges are in graphite and what the edges are in graphene. And usually they're terminated either by hydrogen if it's available or hydroxyl groups. So especially with our stuff where you already have carboxylic acids and hydroxyl groups, one of the things that I should tell you is if you hit this with a laser, you may ask, what's the carbon content at the end? Because the graphite oxide is 30 to 40% oxygen, okay? When we're done at the end of the day, we do this in air, we routinely get 99% carbon, 1% oxygen. We've actually got in air, the best we've ever done is 99.7% carbon. So it's amazing how well these deoxygenate. Now, where is that oxygen? Well, I think a good amount of it is on the edge as hydroxyl and carboxylic acid groups. But it's hard to know. I'm not a surface scientist, and I haven't spent a long time analyzing those edges. But clearly they're important because it's how the things stick together and what's on the edges that will determine how well these things do. And I had this conversation at lunch. You can talk to people who do supercapacitors, and you can say, supercapacitors, have a little bit of degradation. They can go millions of cycles, but they lose a little bit of capacitance. If you're in the battery industry, you look at them and you're like, wow, that's amazing. But then you can ask, why do they degrade? And they degrade because of impurities. It can be oxygen impurities, it can be metal impurities in the carbon. So I once said, I can solve this problem. I can make it much better. And the people at Maxwell and other places said they're not interested because supercapacitors aren't used that way. They're simply used for lots and lots of recharging. And if they have some self-discharge properties, they don't care. So the edges, of course, to chemically and physically are very important. But for people who do supercaps, they don't seem to be that important. So I just haven't spent that much time on it. But it's a good question.
Okay, well, thank you very much, Rick, for your
It's fun. Hi.
Hi, sorry to Philip, physics professor.
Good to meet you.
Have you ever tried e-beam writing